In this video, we're going to be studying infinite sequences. This is a very important topic in Calculus 1, and simply put, an infinite sequence is an infinite list of numbers. These numbers are real, and we're going to call them a sub 1, a2, and so on, such that for every n, a natural number, there exists a real number a sub n. Let's look at the actual definition of a sequence. An infinite sequence is a function of the real numbers with domain in the natural numbers. So if we have a function a that goes from the natural numbers into the set of the real numbers, then this function has R as its image and natural numbers as the domain. Then this function is a sequence. To evaluate the function a, we have to take natural numbers. So we're going to evaluate a in number 1, a in number 2, and so on, a in numbers natural n. And these numbers, the ones in the set of the real numbers, are the ones we call a sub 1, a sub 2, and so on, a sub n. So these numbers are forming the sequence. The notation we usually use for sequences is this one. We use curly braces, a sub n, and then say which variable is moving in this sequence. The thing that's moving is this argument here, and that is the n. We can write it like this. Also a sub n with n in the set of the natural numbers, or we can just simply say a sub n. Let's have a look at a few examples. Let's say we're given the following sequences. The sequence formed by n. Another one is minus 1 to the power n. And the last one is 1 over n. Note that all these sequences depend on n. So what we're going to do is call this sequence alpha sub n. So alpha sub n is n for every natural number n. This one is going to be called beta sub n, and it's minus 1 to the power n. And the last one is going to be gamma sub n, which equals to 1 over n. So what we can do to visualize these sequences is plot them. So we're going to draw the axis for all three of them. Let's start with this one. So the definition said that alpha 1, the first number in the sequence, is going to be alpha evaluated in the number 1. So in this case, we have to substitute n with 1, and that gives us 1. Now alpha sub 2 is going to be 2. Alpha sub 3 is going to be 3, and so on. So now we can plot these numbers here, where this axis will represent the numbers n we are evaluating our function alpha sub n at. So the vertical axis will be alpha sub n. Now, for number 1, alpha sub n has a value of 1. For the number 2, alpha sub n has a value of 2. And so on with 3, 4, and it will always look like this. Let's now move on to this one. Beta sub 1 is beta evaluated in 1. That is minus 1 to the power, instead of n, I have to use 1. And this is minus 1. Beta sub 2 is going to be minus 1 to the power 2, and this is 1. Beta 3 is minus 1 to the power 3, which gives us as a result minus 1. And so on. When we continue evaluating the natural numbers, we're always going to get betas of n to be minus 1 if n is an odd number, and to be 1 when n is an even number. Here in these points, beta starts being minus 1, then it's positive 1, in 3 is again minus 1, and in the 4, because it's even, it's going to be 1, and so on. We'll always get this plot. Remember that the horizontal axis was number n, and the vertical in this case is betas of n. Now let's think about the gamma. Gammas of 1 is gamma evaluated in 1, and that is using n equals to 1, so it's going to be 1 over 1, which equals to 1. Gammas of 2 is going to be 1 over 2. Gamma 3 is going to be 1/3, and so on. So what's happening here is, in 1, gamma was 1. In 2, it was 1/2. Then it was 1/3. Then it's going to be 1 over 4. And so on. It's always getting closer to 0. So what we can see here is that this first sequence is going towards infinity. When n grows, my sequence is also growing. Now for beta, we start at minus 1 and we go positive to 1. But then we can go down towards minus 1, and this cycle is always repeating. But now for gamma, we're always going down, but it's not actually being negative, because it's impossible for 1 over n to be negative, and 1 over n is always positive. So what's happening here is we're getting smaller and smaller, but always above the 0. So we're actually getting towards 0, and it makes sense, because when n is big, we can think of 1 over n as being as close as 0 as possible. And this is a definition we're going to call limit. And this is the definition of a limit. We have a sequence, a of n, and we say that this sequence converges to L. This is how we're going to write it: the limit when n goes towards infinity of our sequence equals to L if for every epsilon greater than 0, notice this, for every epsilon greater than 0, there exists, so here we have every, and now we have existence, a natural number n, such that, again, for every natural number n small, when we have that n is smaller to n, then the absolute value of my sequence minus the limit L is smaller to epsilon. So let's see what this definition is actually telling us, because it's not actually very intuitive until you completely understand it. So we have first, for every epsilon greater than 0, so let's take one epsilon, let's say given an epsilon, and epsilon is going to be a distance, it's going to be a measure. This is a special height with measure epsilon. Epsilon can be 1 centimeter, 1 meter. In this case, it's going to be this orange unit. So we ask ourselves, does there exist n such that if n is greater to n, then a of n minus L is smaller to epsilon? We have an epsilon. This epsilon was given. And we ask ourselves if there exists an n such that this happens. If for every epsilon we graph there exists an n, so the answer to this question is positive, then we can say that the limit of a sub n when n goes towards infinity is L. Let's look at this with a plot. We have a sequence. Let's say our sequence does something like this. And it gets closer and closer to this point here, which is going to be the thing we believe it's the limit L. So what we do is we grab this distance epsilon and place it here. This is epsilon, and here again epsilon. Why is it we do this? Well, if we have a look at the inequality, we want to find this n such that if n small is greater to n, then a sub n small minus L is smaller to epsilon. We can rewrite this as minus epsilon smaller to a sub n minus L smaller to epsilon. And now adding L on all sides, we get L minus epsilon smaller to a sub n smaller to epsilon. So now these points are the L plus epsilon and the L minus epsilon. So what we want to see is if a sub n, if our sequence is between these two numbers, for every small n that's greater to some n we have to find. If this happens, then we can say this limit exists. To see this more clear, I'm gonna draw these two horizontal lines. And now notice this point right here. Let's call this number n. Well, we want to see if for every small n, remember that the horizontal axis was the n axis and the vertical one was the a sub n. We want to see if for all n bigger to n, that is for all the points, all these numbers, these are all n greater to n, we want to see if this happens, if a sub n is between L minus epsilon and epsilon, and I forgot to add L here. Does this happen? Well, let's see. If we draw a vertical line here, we find this element. This element is the a sub n, capital N. This is a sub n plus 1. This is a sub n plus 2, and so on. We have all these are a sub n's with n greater to n. And if you look at the plot, then we can say that all these numbers are between these two lines, the lines L plus epsilon, and this one, the line L minus epsilon. So now what we should do is start moving the epsilon, because we took a particular epsilon and proved that there exists an n. Which one is it? This one. Such that if n is greater to this n we found, then the sequence a sub n is between L minus epsilon and L plus epsilon. So now we have to do this for every epsilon greater than 0. So if we took a smaller epsilon, I'm gonna do it in another color. Let's say I took this other epsilon. So I would have to put it here and draw the two horizontal lines. Well, now can we find another n that satisfies this? Yes, I can, because if I take this one, this n, then all these other elements are between the two green lines. And so in this case, we can say when we've tested for every epsilon, then we can say that the limit of this sequence a sub n is L. This might still sound a bit complicated, so what we're going to do is, as usual, work with an example. And this example is going to be the one we saw before. Gamma sub n is the sequence 1 over n. We want to prove that the limit when n goes towards infinity of gamma sub n, this is the limit when n goes towards infinity of 1 over n, we want to prove that it's equal to 0. So the first step was to take a number epsilon greater than 0. We take a distance. This epsilon is a real number. And what we want to do is we want to find n, a natural number, such that if we take another n that is greater to n, then my sequence gamma on these numbers n minus my limit, in this case, is 0. This is gamma sub n was 1 over n minus 0. We want to see if this is smaller to epsilon. Now the trick to do this is, let's start with this. Let's start with the thing we want to prove. We know this is mathematically wrong, but you'll see where I'm going with this. So we start with, suppose we have found an n, and n is greater to this n and satisfies 1 over n is smaller to epsilon. Then minus epsilon is smaller to 1 over n, smaller to epsilon. Now let's multiply by n, so we get minus n times epsilon. This will be smaller to 1 and smaller to epsilon times n. Now we can divide by epsilon, so we're going to have 1 over epsilon. And this number is going to be between minus n and n. So now one thing we can do is take our number n to be the ceiling of 1 over epsilon. N is a natural number, so we are under this hypothesis. And then what happens is that if I take n greater to n, as n is the roof of this, then n will be greater to 1 over epsilon. And if n is greater to 1 over epsilon, then 1 is greater to 1 over n times epsilon. And then multiplying by epsilon, we get that epsilon is greater to 1 over n. But this is actually the one we wanted to have. So this is just to get an idea of what big N to take. But then we say, just given an epsilon, take this n, the ceiling of 1 over epsilon. N is a natural number, and when we grab another n that's greater to this one, then what happens is that epsilon is greater to 1 over n. And this is what we have here, and so it's the definition of limit. Then what we can say is that the limit when n goes towards infinity of 1 over n is actually 0. Now let's move on to see another definition. This is also a very important definition. We have a sequence, a sub n, and we say that this sequence is bounded if the set formed by all the numbers in this sequence, so a sub n was n, a natural number, that is just the definition of a set that collects all the numbers a sub n. So if this set is bounded, then this sequence is bounded. And what this is that there exists a number, a real number c, such that the sequence a sub n is always smaller to c with absolute value, so it can be negative or positive, but it's always between minus c and c. And this happens for every natural number n. Visually, what this would mean is, let's draw the axis. If the sequence we take is bounded by here by c, I'm going to draw the negative c also. So this is c and this is minus c. And we have this sequence a sub n. Then all the numbers in our sequence are here. It doesn't matter if they're closer or further away from the axis and from c and minus c, but they are bounded by c. So it cannot happen for one of the elements of A to be here. This cannot happen. They are always between minus c and c. And now with this definition comes a very useful proposition. This is a very important proposition, and it says that every convergence sequence is bounded. Remember, convergence sequence was that it had a limit. If a sequence is convergent, then it is bounded. Let's try and do now the proof for this proposition. So, what we know is that we have to start with a series that's convergent. So, let a sub n be a convergent sequence, that is, a sub n tends to a number L. This is another way of writing that the limit when n goes towards infinity of a sub n equals L. These two symbols represent the exact same thing. So what we know, because of the definition, was that for every epsilon greater than 0, there exists n, a natural number, such that if n is greater to n, then a sub n minus L is smaller to epsilon. And this happens for every epsilon. So take epsilon equal to 1. As this happens for every epsilon, in particular, it will happen for epsilon equal to 1. Now, we want to prove that A is bounded. So what we have to do is find a number c such that a sub n is smaller or equal to c. So let's start by saying what a sub n is. And what we can do here is write this as a sub n and subtract L from this expression and then add it again, because this equals to 0, so the equality still holds. Now we can use the triangle inequality and rewrite this as saying that this expression is smaller than or equal to a sub n minus L plus the absolute value of L. We don't know whether L is positive or negative, so there is nothing we can actually do with this expression. Now, as we said before, a sub n tends towards L. So then, using the definition, we know that a sub n minus L is smaller to epsilon. We know this happens, and this happens for every epsilon and for every n that's greater to some number we know exists. And that's natural. And in particular, we were taking epsilon equal to 1. So what we're going to do is, we know that a sub n, because of what we have here, is smaller or equal to a sub n minus L plus L. And because of what we have here, we can make this one smaller and say that this is smaller to 1, because epsilon was 1, plus this other thing, plus the absolute value of L. And we can just call this C1. C1 is the absolute value of our limit plus 1. And this is valid for every n that's greater to some capital N. Now, if we remember the definition of boundedness, then it was for all natural numbers. And for now we only have the bound for some of them. It's most of natural numbers, but we have still n numbers we are not taking into consideration. So what we're going to do is create another set B. This set B is going to be formed by all the numbers in my sequence up to the number n. So all the numbers I'm not considering in this inequality. B is finite, because P equals a sub 1, a sub 2, and so on until we get a sub n. And as it is finite, then it's bounded. Because being finite means it has a maximum value. Let's call this value C2, the maximum of the set B. So this is the maximum of all the numbers a sub n such that n is smaller than or equal to the capital N we got from our epsilon equals to 1. Now let's call C equal to the maximum between the two bounds we have, between C1 and C2. So C is greater than or equal to C1 and also is greater than or equal to C2. So we have that a sub n is smaller than or equal to C1, smaller than or equal to C for every n greater to n. And also a sub n is going to be smaller or equal to C2, which also is smaller than or equal to C for every n that's smaller than or equal to n. And now with these two things we have that a sub n is smaller than C for every natural number. So we were able to find C, a real number, for which A is bounded. Now the trick for this was first using the definition of the limit, because what the limit tells us is that starting here with some natural number n, my sequence was going to be bounded by some number C1. But I had no idea what was happening with my sequence here. But it could have been very crazy. It couldn't have enormous values, but finite values. So what we did is just say, hey, this is the greatest value of all. So just bound all these elements with this other number C2. And now take the maximum of these two numbers, C1 and C2. In this case it was C2. So just call this C. And now all my sequence is between these two lines, and so my sequence is bounded. Let's have a look at one final theorem. This is a very well-known theorem. It's called the sandwich theorem. We'll see when we finish with the proof why it's called like this. So we have three sequences, a sub n, b sub n, and c sub n. And they have this relation, a smaller to b and b smaller to c. But also a and c have the same limit. So the sandwich theorem tells us that B, the one here, must have the same limit. Let's prove this. The information we have is about the limits of A and C. So let's start with the definition. Let epsilon be a number greater than 0. We know that there exists n, a natural number, such that for every number n that's greater to this n, two things will happen. First, the limit of A is n. So a sub n minus L is smaller to epsilon. And also the limit of C sub n is L. So C sub n minus L is smaller to epsilon. What this is telling us is that minus epsilon is smaller to a n minus L, smaller to epsilon. Then L minus epsilon is smaller to a sub n, smaller to L plus epsilon. And the same here. Now we also know that a sub n is smaller to b sub n and smaller to c sub n. So and now here we have that L minus epsilon is smaller to a sub n. So L minus epsilon is smaller to a sub n. And here we know that C sub n is smaller to L plus epsilon. A sub n was smaller to B sub n because of our hypothesis. And B sub n was smaller to C sub n also due to our hypothesis. So now L minus epsilon is smaller than or equal to B sub n, which is also smaller than or equal to L plus epsilon. Subtracting L, we get that minus epsilon is smaller than or equal to B sub n minus L, smaller than or equal to epsilon. And we can rewrite this as B sub n minus L, smaller than epsilon. And this happens under this hypothesis. This is for every n that's greater to n. And this is the definition of a limit. So then the limit when n goes towards infinity of b sub n equals L. Now, why is this theorem called sandwich? I'm going to be drawing the sequences as lines because it's going to make it more clear. But if we have this sequence, C sub n, and this other sequence, a sub n, they both have the same limit. But now we know that B is between these two sequences, so B can do whatever it wants, but it has to stay between these two. And in infinity, the limit must be the same. So we're actually making a sandwich with A, B, and C. And that's why it's called the sandwich theorem.